we go. So thank you everybody for coming. This week we have Ms. Aziza Al-Rajid speaking to us about zeros and harmonic polynomials and related applications. One of the applications I'm very interested in is called gravitational lensing. So please welcome Aziza. Thank you for talking, and well, Aziza, it's all yours.
Okay, today we are going to talk about the harmonic function and the maximum number of zeros for this function. Also, we will see some application related to this concept. Let's see. So I talked in chapter 1 about the history of harmonic polynomials and rational harmonic polynomials and gravitational lensing. Then in chapter 2, we discuss what kind of coefficient or which conditions we can put in the coefficient when we have harmonic polynomial of degree 2 equal to z bar squared. And we will see when this coefficient are real or complex. Later on, we jump to the idea of gravitational lensing, and we discuss different kind of lens as ellipse, limacon, Neumann Oval. So in chapter 1, for harmonic polynomials, we start with the idea of fundamental theorem of algebra, which state that every complex polynomial of degree n has precisely n complex roots counting multiplicity. In 1992, T. Shell Small, he was wondering, what about if we change this complex polynomial with a harmonic polynomial? How many zeros we are going to get? First of all, the complex function means that the function satisfies Laplace equation and the first and second partial derivatives are continuous. And by replacing z by x plus iy and z bar with x minus iy, we can rewrite any harmonic polynomials as you see in equation 1, where b and q are analytic polynomials. Even when you have z and z bar looks, it doesn't affect our polynomial, but it will play a big role on the maximum number of solution for h of z equals 0. For example, if we consider h of z to be equal zn minus z bar to the power n, and we write z as equal re to the power I theta, where theta is between 0 and 2 pi. This will lead us to have n equal space lines through the origin, which give rise to infinite number of solutions. Sorry. T. Shell, with his student, keeps studying this concept about the maximum number of zeros for harmonic polynomial, and they conjecture that it will have at most n squared zeros. In 1994, Schwarz, he proved that any harmonic polynomial could have at most n squared zeros by using Beneteau's theorem. Beneteau's theorem states that any complex valued polynomial written in this way, where u and v are real functions of degree m and n respectively, and they are relatively prime, then b has at most m times n zeros in complex plane, which is mean Schwarz, he rewrite the complex polynomial as curves, and he saw the intersection and he count them, and it gets n squared intersect. Later on in 1998, he proved that the harmonic polynomial, when it has degree n for b and n minus 1 for q, it will have at most n squared as a sharp zeros. And he conjectured that if m is between 1 and n minus 1, so our harmonic polynomial will give us at most 3n minus n plus m times m minus 1 zeros. For this particular case, if we consider m to be 1, in 2001, Cham and Schwarz, they prove this conjecture is true. Additionally, they prove it's sharp when n is equal to. Until 2008, Gary, he proved the sharpness for every n by using the work of Sarson and Croft. In 2016, Cham and Lee and says they got sharper version of Wilm-Short theorem, where they prove for real coefficient for our harmonic polynomial, there is n squared minus n solution when the real part of z times the imaginary part of z doesn't equal 0. While they said for every n greater than m, there exists a harmonic polynomial with at least 3n minus 2 or m squared plus m plus n roots. Also, other mathematicians keep looking for the problem, trying to prove or disprove Williams conjecture until 2013 by using algebraic geometry. Lee and Lero and Landberg, they prove there exists an analytic polynomial b and q of degree n and m respectively, and they get this formula to show like the conjecture is not true in general. Still, regarding to the question of how many zeros we will have for harmonic polynomials, it's still an open problem. Nobody solved it up to now. In 2006, Cham and Neumann, they study what happened if they replace our harmonic polynomial with a rational polynomial and how many zeros they can get, where r of z written as b of z over q of z, and the degree of r is the maximum between the degree of b and q. They prove that it will, the maximum number of zeros, it will not exceed 5n minus 5. And this kind of problems, it's related to gravitational lensing. At the same time, Rehi, who's our astrophysicist, she proved that this result is sharp for every n by using some simple geometric construction. As you see in this figure, what's happening, we have a source plane and lens plane and observer. So the light deflected due to the gravitational force of the lens, which implies the observer see multiple images. So the equation which connect the position of a light source and the lens and the mass distribution of a gravitational lens, such as galaxy, to the number of images that we will have, called equation, lens equation. As you see in this picture, sometimes we have bright images or dim images which we can notice.
What?
It's not on the headphones.
How do I do headphones?
Emo, you're not muted. 1 second.
Hi.
Hey.
Okay. So regarding having z inside the domain or outside the domain, that's if z inside the domain, we will have dim image. If it's outside the domain, it will be bright image. As you see in this equation, that's the formula of lens equation, where W denote the source position and Z is the position of the lensed image, and ZG is the position of the point masses, and all of them in the complex plane. That's if we consider the point mass distribution. But if we look at it as continuous mass distribution, the lens equation becomes in this formula. As an open problem, we still unknown how many zeros we will have for r of z equals z bar to the power n. Later on, as I said, we will study the condition on the coefficient where we have this equation b of z is polynomial of degree, analytic polynomial of degree 2, and any polynomial b of z equal q bar of z could be rewritten in this way by some algebraic operator and by change of variable. So for real coefficient, if we have az squared plus bz plus c equal z bar squared, where a is not 0, we will have the following conditions. And this condition created when we try to rewrite our complex polynomial as a system of real equations, and we try to solve it. Notice that when a is equal 1, we will have one solution. And when A is equal -1, we will have even two solution or no solution, as you will see in the following figures. Here, this green line represent the real part, while the red lines represent the imaginary part, and they intersect just in this point. For A equal -1, we have this condition to be satisfied. As I said, if it's satisfied, we will have two solutions. As you see, the curves intersect the red line. And here they are not intersecting because it doesn't satisfy our condition. And here's some.
Sorry. So the intersections are the lensed images, yeah?
Yeah, the number of images.
So the number of intersections. Okay.
Okay. Here we're trying to see if we satisfy the condition I put it or not. As I said, here you can tell not satisfying give you two solutions, not satisfying give you two solutions. Here, because it satisfies the condition, 1, 2, 3, 4 solution, and that's the maximum. Because as I said, n squared, that's mean 2 squared, which is 4. The same for here, and that's the final. So now, if we consider we have a complex coefficient, by the same technique, rewriting those as a real, as a system of real equation and studying the coefficient, we will have the following conditions. Still, even if B equal, like the degree of B is 2, having the condition, it wasn't easy. So we're still with an open question. What about if B has a degree n? What is condition we can put on our coefficient for this polynomial to get the maximum number of solutions? Now we will see how this related to the lens or the gravitational lensing problem. In 2009, this mathematician investigated the number of solutions to the lens equation for an ellipse shape with the uniform mass density. If we consider our lens, which is the ellipse, given by this omega, has an area AB.
I'm sorry, Aziza, but there is only one of the three is a mathematician, actually.
I'm sorry?
There is only one of the three is a mathematician, myself. The other two are physicists.
Okay, I'm sorry for that. Thank you for correcting me. For this lens, as we said, this our omega has an area AB times pi, where A greater than B greater than 0, and gamma is the boundary of our ellipse. So the lens equation will be given by this equation, where we have normalizing 1 over pi to get an area 1. To be able to calculate this integration, we have to transfer it to line integral by using Green theorem, which stated as follows. If we have a continuous function with a continuous partial derivative in a region R and on its boundary C, then we have this integration where D of A represents the element of the area. As we mentioned before, having Z inside or outside the domain will affect the images. So when Z is outside the domain, our integration could be written as equation 10, while if it's inside the domain, it will be written in this way using Green theorem. As you can see here in this integration, we have zeta bar. It's not analytic function along gamma, so we have to replace it with analytic function. To do that, we define the Schwarz function for our lens. Schwarz function is a function equal to z bar along our boundary and satisfy the conditions, as you see. The Schwarz function for ellipse could be calculated from the ellipse equation by substituting instead of x, zeta plus zeta bar over 2 and zeta minus zeta bar over 2i. And this equation is quadratic equation, could be solved by using the quadratic formula. Just to ensure that we have an analytic function, we have to make the branch cut inside the ellipse between minus c and c. Now, we have to choose zeta to be in gamma. For this reason, we choose zeta on gamma, and we substituted on this equation just to make sure which sign we are going to get, the positive or the negative. As we've seen, by choosing the negative sign, we get zeta bar on gamma. So we will have the Schwarz function written in this formula. And as we explained before, the zeta bar will be replaced by the Schwarz function, as you see in here. I'm sorry. The first part, it will be my psi 1. The second part, it will be my psi 2. Rewriting the length equation, it will become in this formula by integrating the first part where psi 1, zeta 1 is psi 1 over zeta minus z, it's analytic. And by using Cauchy theorem, it will be 0. While for this one, we will use Cauchy integral formula, which will give us psi 2 for z. As you notice here, we have square root. So we will squaring both sides, and we will have a system. If we rewrite z as x plus iy, we will have a system of two real equations. And by using Beneteau theorem, we will have at most 4 solutions for z outside the domain. While for z inside the domain, we will calculate the integration again. One by Cauchy theorem will be 0, and the other one by Cauchy integral formula. By Cauchy integral formula will be psi 1 of z. So we will have a linear equation of one parameter, which lead us to have one solution. So the author said, an elliptic lens, say galaxy, with a uniform mass density may produce at most 4 bright lensing images and 1 dim image inside the domain. So we will have in total 5 images. As a remark, we notice that having the sharing term will not affect the number of solutions, as we will see in the other lenses. In 2018, Beneteau and Hudson were interested about the number of solutions of the length equation if they change it with a limacon shape instead of ellipse. And they follow at the beginning the same technique where they mention what is the omega, the limacon length, and the area of it, and gamma, it will be the limacon. And here our normalizing will be 2 over 3 by dA of zeta. That's our length equation. The same procedure. We will calculate this integration by using Green theorem at the beginning. Then we will try to find the Schwarz function, which is quadratic equation, and we will use the quadratic formula. Then we have to decide which sign we will get for our Schwarz function. But before that, to make sure we have an analytic function, we have to make a branch cut. So for simplifying, they assume that a squared minus b squared over 2b is a, and they said they will have the branch cut along the ray from minus infinity to minus a. So our zeta bar will be written in this form, where psi 1 of zeta equal to this, and psi 2 of zeta equal to this. And as you notice here, we will have both at b over 2. So zeta 1 is analytic in C, except at this point, and psi 2, it will be analytic in gamma, sorry, in omega, except at b2, b over 2, which lays inside the domain. As we did before, we will write zeta bar as a Schwarz function by using Schwarz function. Then here we will use the residue theorem. For z is not in our domain, by using residue theorem, we get 1/2 by I equal to this, while when Z inside the domain, we have to use residue theorem for B/2 and Z. And we have this. So they wrote the theorem that suppose if we have omega is the interior of limacon with a constant for A greater than B greater than 0 with a constant mass density, as you see, we will have the length equation for Z not inside the domain, and the other one is for the Z inside the domain. As you see in equation 17, that if we consider the sharing term is present by Hudson and Neumann theorem, that's we will have a rational function of degree 3, which is mean we will have at most 10 solutions, while by Beneteau theorem, we will have 9 solutions. But if we consider the sharing term to be 0, by Hudson and Neumann theorem, we will have 5 solutions at most, while by Beneteau theorem, it will still 9 solutions. So what they said we will have 9 solutions if the sharing term is not 0, and 5 solutions if the sharing term is 0. If you look for equation 18, there is a square root, which make us have to simplify it to the point where we square it. So most likely we will have overestimate solution. So for this equation, we can't use it Hudson and Neumann theorem because it's not rational anymore because of this square root. So I'm sorry.
I have a question, I think. So for the one above, I think it's equation 17.
Yes.
So if the sharing term is 0, you're saying there's at most 9 solutions, yeah?
I said there is 2 theorems to analyze this equation, even Beneteau or Hudson and Neumann theorem. Okay.
Okay.
For call it, for example, the rational theorem. For the rational theorem, look, if that's is 0, so the whole term is not there. So the degree is 2.
Mm-hmm.
And we said 5n minus 5, which is make it 5 times 2, 10 minus 5, it's 5.
Okay. But if it's there, okay, I see. So there's more solutions, yeah?
Yes, yes.
So is it, maybe you say this later, but is it sharp? So do you find maximal number of solutions attained for particular A and B's and gamma?
For this case, no, we didn't find a sharp one. Maybe for the last one, the modifying normalizing factor, you will see the sharp one.
Okay, cool. Thanks.
Yeah, okay. So they wrote this theorem, which omega is the interior of the limacon with a constant chosen, so that A greater than B greater than 0 with a constant density. Then, as we said, we will have 9 solutions for equation 17 if the sharing term present, while 5 solutions if the sharing term is vanished. While for equation 18, we will have 16 solutions if the gamma is not 0, 12 solutions if the gamma is 0. The author of this article, they mentioned that the expected number of solution of equation 18 is overestimate, as we explained. And they make the conjecture that if we have this omega with this normalizing factor, we will have at most 1 solution of the length equation 17 and 4 solutions for the equation 18. We found a counterexample for this conjecture. As you see here, I'm not sure if it's clear enough. We have 1, 2, 3, 4 solution when gamma is 0. And here we have 6 solution with gamma not 0, while they said there is just 1 solution. And also, if they consider for gamma is 0, they consider it for gamma is 0. What about if they study when gamma is not 0 for the same parameters? They can get 3 solutions at least. For equation 18, which is studying Z inside the domain, we will have 4 solutions when gamma is not 0, while we have 2 solutions when gamma is 0. So we wrote this conjecture that equation 17, the Lens equation, we will have 6 at most when gamma is not 0 and 4 at most when gamma is 0. Moreover, there is at most 4 solutions inside our domain when gamma is not 0 and 2 inside the domain when gamma is 0. Now, we will look for a different lens, which is Neumann Oval. Gamma for Neumann Oval described as follows, and it has area 2 pi times a squared plus 2 times b squared. And gamma is the boundary of Neumann Oval, and also the Lens equation could be written in this formula with 1/3 pi normalizing factor. By following the same technique as we did in Ellipse and in limacon, we're trying to find the Schwarz function, and we have the quadratic equation. We solve the quadratic equation, and now we have to decide which where we will make the branch cut to make sure we will have analytic function, and we end up by having this branch cut should be outside the domain. And now we want to decide which sign we are going to take, and we figured out it should be the positive sign. So our Schwarz function could be written as follows. If psi1 could be written in this formula, and if psi2 could be written in this formula. And by using, again, the Schwarz function to calculate the same integration, we have, by using residue theorem, the following theorem. I didn't go over it slowly because it's the same technique as limacon, residue theorem, and the same thing. We conclude the same theorem, but different equations. So we will have equation number 20 and 21. It's the same discussion for number of zeros, but here we make a conjecture that we will have, because we go through numerical experiment, as you can see here, for Z outside the domain, we will have 5 images, while if the sharing term for the first image, it was the sharing term not 0. Here, the sharing term is 0. We have just 1 solution. All of this just numerically, because we couldn't solve it and get the exact solution. While if we have the Z inside the domain, so we will have 4 images when the sharing term is not 0, and 2 images when the sharing term is 0. As a conjecture, we wrote the same information, that we will have 5 solutions outside when the sharing term is not 0, while we will have 1 solution outside when the sharing term is 0. Also, there is 4 inside if the sharing term is not 0, and 2 solutions when the sharing term is 0. The last section, we will consider a special case of Neumann Oval. As you saw before, the Neumann Oval, it have been written as a squared cosine squared theta plus, sorry, for b squared cosine squared theta plus a squared. So if we assume that a squared is 1 and 4b squared c squared minus 1, where the absolute value of c greater than 1, we get a special case of Neumann Oval. And if we look for Neumann Oval as overlap 2 ellipse and modified the normalizing factor from 1/3 pi to 2 pi, we will get different number of images. Actually, we get the sharp number of image for this equation. It will be slightly different, the equation, just here, the normalizing factor is different. And for number 25, it was zbar plus something. Now it's minus zbar plus this thing, and we will deal with it as previous. So, as we said, we have 9 solutions for outside when sharing term is not 0, and 5 images when the sharing term is 0, while there are at most 16 solutions to the Lens equation if the sharing term is not 0, and 12 if it's 0. as I said, we will have 9 solutions at most. That's the sharper thing we could get. 1, 2, 3, 4, and 5, 6, 7, 8, 9 when the sharing term is not 0. And here it's 5 when the sharing term is 0. While for the inside, I couldn't get to the 16 images. I got, when gamma is not 0, 8 images, and here 4 images. So as a conjecture, suppose that omega described as follows: the interior of a Neumann oval with a constant mass density and with this normalizing factor, then there is at most 8 solutions inside when gamma is not 0, and 4 solutions inside when gamma is 0. And we can note that I put as a condition that absolute C should be greater than 1. What about when absolute C is less than 1? We will have a shape looks like a Neumann oval, but in different axes. With the same calculation, we will get the same theorem. And by numerical experiment, we couldn't get any more images. It will be less. Actually, while we are doing this work, we try to investigate the number of images for other lenses as rose curves, spirals, Cassini ovals, but all of them, the Schwarz function to find analytic Schwarz function along the gamma, it wasn't easy. And also it's possible to study the coefficient on the condition for our equation as we did in chapter 2. Finally, I'm wondering, like, is there any relation between the normalizing factor and the maximum number of images that we can get from each lens?
So
And those,
question about that, actually, could you go back? So by this last remark, you mean changing the density so that you have uniform density, but the
as we did for normalizing factor, as you see here.
so like 1/3 pi versus 1/. Okay.
Yeah,
okay.
1/3 pi doesn't give us a sharp example, while 2/pi give me the sharpness. So do you think there is any relation between the normalizing and the lens equation or no?
Okay, that's an interesting question.
And those the resources, the references. We thank you. That's it.
So let's thank our speaker really quick.
Thank you so much.
Where's the clapping? It's here. There. So does anyone have any questions? I have a few, but maybe other people have questions first.
I did have a really quick one. So my question is, have you gone over any research that extends some of these results into maybe arbitrary dimensions? So instead of complex plane, maybe into Rn
Jesus.
or into, I think you knew that was coming, Dr. Cavinson.
Could you repeat your question? I'm sorry.
Have you come across any research that takes these results and maybe extends them to similar results or comparable results in Rn or maybe into Cn or something like that?
I believe that for Neumann Oval, I can't remember his name. I'm sorry, this guy,
Lundberg?
Yeah, he did some research for Neumann Oval in R4.
Interesting.
Yes, I believe so. It was in his thesis.
Okay.
With Dr. Dima.
Okay. And I guess just one more question. So you mentioned that a lot of these are for harmonic functions. Have you extended that to things like, say, p-harmonic functions, which is the next obvious question from me? Yeah, and I can see Nathan's face.
No, I didn't.
All right, just out of curiosity. Thank you so much.
Yeah.
All right, can I say something about?
Yes, sure.
Yeah. Okay, first of all, it's Neumann, not Newman. It's Harry Neumann.
Sorry.
It's German. He's German, was German.
Okay.
Secondly, as far as not two-dimensional problem, Eric actually didn't do anything in higher dimension. Eric was, in fact, my student. But his student did very recently, Sean Perry. It's a much more difficult problem. And before that, Arlie Pathers, who is a professor at Duke, did this. And because complex analysis goes out and therefore very limited technology to count the solutions of that equation. And the equation becomes not one equation, but system of equations, because what you have to write is a gradient of Newtonian potential equal to identity vector field. And then it comes very close to very famous Maxwell problem of the number of equilibrium points, which is, well, Maxwell had no problem claiming the result, but it's still unproven. It's still not known whether he was right or not. The last thing is about not everything that is true for harmonic functions should be immediately thought of for p-harmonic functions or whatever, because the problem is, the problem comes from a very natural setting in astrophysics. And until it's sort of settled on a deeper level, it should stay there instead of just, you know, plus p-harmonic functions, they, well, it depends. The argument principle, which governs everything in some sense, is much more complicated for p-harmonic functions, and zeros are not necessarily isolated. So it's, I mean, it's a legitimate probably questions for p-harmonic polynomials, but to get even an example of p-harmonic polynomials, John Lewis 30 years ago wrote the whole paper on it. So it's you can't just write down a polynomial which is p-harmonic. Well, you have to work very hard. So I don't think it's kind of question for modern times. It's maybe for 100 years from now.
Appreciate it. Thank you. You're 100% right. It's such a more complicated problem once you start extending the dimension or going to p-harmonic, but it's my curiosity every time I hear about harmonic functions or complex problems. Thank you, both of you.
Thank you.
Thanks for the commentary, Duma. Any other questions or comments? So maybe I'll ask, so I think Aziz actually you answered a couple of mine already. So one was about the, if you change the actual fixed constant in front of the density, what happens? And I think you pointed out that it's not like an obvious question. The other one I asked was just like other shapes of interest. And I think you said that it's just difficult to actually write down Schwarz function for some of those things.
Yes.
That also you answered. But the third question I have, I think is maybe, I thought about it, and I think maybe it is non-obvious. Because I don't think you can use complex analysis for it. So if you have non-uniform mass density, so you have a shape like Neumann Oval or
Okay.
lemniscate with non-uniform mass density on it. Do you have any comments about what happens in that case, or was it anything you considered or anything? Like, to me, it seems like it's not an easy question just because you can't immediately apply Schwarz function techniques. But
if we have a Neumann Oval shape, you said.
And non-uniform mass density. So you put density at the top instead of just constant, like rho of z dA or rho is positive function.
I didn't think about this before.
Okay, can I make a comment on that?
Yeah, please.
Yeah. Well, we're talking about, I mean, the original problem, well, not the original problem. The original problem is polynomials, which is not solved and far from being solved. But the gravitational lensing problem is physical problem. Out of all people, Nathan. So physicists do not talk about densities in general. I mean, densities should make.
No, but even like slight general, they don't have to be general.
Hold on. Let me finish. So in physics, the assumption is, because we're talking about galaxies, gas in galaxies. So assumption is that the density is such that keeps the temperature constant of the gas. And that density is very simple. It's inverse proportional to the distance to the center of the galaxy. But the problem is you can, I mean, Eric and I did it, and some other people did it for ellipse, and that's a physically much more interesting density than uniform density. The uniform density is just kind of first step, just to try something. So that density, it's called isothermal for this reason, density. You can calculate everything. It's not a problem. The problem is that at the end, when you look at the equation, this Cauchy integral materializes as a transcendental function.
So that's
right. So in particular, for ellipse, it becomes arcsine. And actually, yeah, well, I mean, you know, it's a calculation Eric and I did before he graduated. But so every expectation from Picard's theorem and whatnot, that the number of solutions is going to be infinite. We found, in particular for ellipse, isothermal elliptical galaxy, that the number of solutions not only finite, it's bounded by 8, which we were so sure that we made a mistake, we actually didn't publish it for a while. Then we did, and then immediately Yeremenko and Birkhauser improved a little bit our technique. And first they proved that actually it's bounded by 6, not 8. And it goes against every intuition any complex analyst has, because transcendental, because everybody knows Picard, well, almost everybody, Picard's theorem, which says that a transcendental function takes every value except one value infinitely many times. And so this density is interesting, and it can be calculated, but each time you will end up with a transcendental function, elementary transcendental function.
What was the name? Isothermal density?
I'm sorry?
Isothermal density, you said? There's paper with Eric?
Yeah, isothermal. Well, it's not only Eric, it's mentioned in paper which Aziza mentioned with Chuck Kitten and Fastnacht. It's mentioned in paper, it's certainly done in papers by Birkhauser and Yeremenko, a lot of people. The point is that each time you do something with transcendental equation and you get a number, it's a very good theorem, but it's very hard theorem because, you know, like if you, the point of our approach with rational functions is to use dynamics, which means you can iterate, but it's very difficult to iterate functions like arcsine or sine. It's you know, I mean, there is still dynamics, complex dynamics for those functions, but it's very difficult. So, but that's the density worthy of the name. I mean, uniform density is kind of to start the game. I mean, you have to start somewhere. So, but that's not what happens. Galaxies do not have uniform. Well, I mean, just think about it. Galaxies are filled with gas, and certainly at the periphery, there is less gas than at the center of the galaxy, right? I mean, that's pretty obvious. And the physically legitimate density is 1 over the distance to the origin.
Okay, so that's interesting.
It is, and it's elementary, and each time you calculate something, it's a paper. So it's a, I mean, you know, it's not that anybody is going to get Nobel Prize in physics for that, because that's not how physicists actually work. They don't really care that much how many images you see. I mean, but what they do care whether you see infinitely many or finitely.
Sure. Okay, that's interesting.
I mean, that's I don't want to monopolize the podium, but
Okay, so while he's on the phone,
yeah.
any other questions from the audience? If not, then let's thank our speaker one more time. So thank you, Aziza, again for coming to speak.
Thank you so much for being there.
Yeah.